Hello again. Alright, so in this video we're going to be talking about quantum numbers again, and we're going to talk about their atomic relationship and how it relates to the periodic table. Okay, I've drawn a very general periodic table right here. Okay, it's just a general schematic, and I've labeled zones on the periodic table, S, P, D, and F, and I wrote the letters up here as well. Alright, so on the left side, and then I'm just going to throw you some factual information first, and then it'll help in the explanation. So on the very left side, we have this rectangle, that would be the S zone. Over here, we have this block over here, that would be the P zone. In the middle would be D, and at the bottom would be the F, okay, as designated by this picture that I've shown. Okay, we're going to be mainly dealing with the S and P zones today. The D and F, they get a little bit confusing, but hopefully we can understand at least the S and the P today. Alright, so before we get into an explanation of what quantum numbers are, it helps to understand what's an orbital. What's an orbital? What is an orbital? Okay, well, an orbital, if you don't know, very generally, is, let's say that's the nucleus of some atom, right? This would be in the electron. And the shape that the electron makes around some nucleus is basically the orbital, okay? And there are two kinds of orbital we're going to be talking about today. Also keep in mind that the maximum amount of electrons allowed per orbital is 2. So I've shown you 2 orbitals around here. There are 2 electrons in here. I cannot draw a third one or fourth one, but the maximum amount is 1. The minimum amount allowed per orbital is 1. But the maximum is 2. Okay? There are 2 different orbital shapes. Okay? What are they? One is spherical. One is a spherical shape. Okay? The other one that we're going to learn today is dumbbell. Is a dumbbell shape. Okay? The spherical shapes relate to S, right? Relate to the S side of the periodic table. So if you haven't heard of the word valence, don't worry about it too much, but we're basically dealing with the valence electrons, or another way you could put that is the outer electrons in these atoms. Okay? And that would be, and again, the spherical electron, or the spherical shape, is present in the s orbitals and is designated by the atoms on the left side. Okay, dumbbell shape would have to be with P. Okay, they have to do with the P side of the periodic table, and a dumbbell shape looks basically just like a figure 8 or some 8. Okay, another thing to keep in mind, and this again is just factual information, there's only one orbital per S shape. Alright, and there are 3 orbitals per P shape. Now, what exactly do I mean by that? Alright, if we look at the atom beryllium, right? It's in the S zone. Okay? Its outer electron shell, if this is the nucleus of beryllium, its outer electron shell, or its outer, or its valence electrons. And if that doesn't make too much sense to you, don't worry about it. Just think of it as electrons. Its electrons are rotating around, or not rotating, but they're not exactly revolving, but they go about the nucleus in a spherical-like manner. And I drew 2 electrons designating that. And it's hard to draw a sphere on a 2-dimensional surface. Maybe I could add some depth. I don't know if that helps at all, but it's basically revolving in a sphere-like manner, right? If we look at, and again, I only showed 1 orbital. If we look at neon, right? Let's look at neon. If this is going to be the nucleus of neon, it's going to have 3 dumbbell orbitals, and that looks like this. Right, so those 2 would be flat in the page, and then the last one, I guess I'll do it in a different color. It would be jutting out of the page in some manner like that. But it has 3 dumbbell orbitals, and each single orbital contains contains 2 electrons. Okay, so that's what I meant by the p orbitals allow for the p shapes allowed for 3 orbitals, while the s orbital only allows for 1 orbital. All right, so now that we have some idea of orbitals, let's get to the quantum numbers. We learned about m, we learned about L, and we learned about m sub L. We learned in the last video that L, or that n, can equal any integer number. But specifically when referring to the periodic table, n is actually the row number. Okay, is actually the row number that you're looking at. So if you were to say n is equal to 1, you'd look at the first row, n is equal to 2, you'd look at the second row, n is equal to 3, third row, and so forth. Okay, when we learned L from last time was just basically 0, 2, n minus 1. So if n is equal to 3, then the possible values of L would just be 0, 1, and 2. Okay? L actually refers to the zones that I showed you earlier. S, P, D, and F. Okay? These zones just happen to be numerical values as well. Or these zones happen to be given numerical values as designated by L. So S would mean L is equal to 0. P would mean that L is equal to 1. D would mean L is equal to 2, and F would mean L is equal to 3. Now again, in this video, we're mainly going to be dealing with S and P. Okay, but just keep in mind. So for instance, if you said n is equal to 2, okay, which means L could be 0 or 1. Let's just take a look. Right? So n is equal to 2. We look at the second row in the periodic table, and it just so happens that the S zone as well as the P zone are both present. Okay? So that's just a way to think about it. All right? Now, what about m sub L? Well, m sub L, we learned, just has values of negative L to positive L. What does that really mean in terms of atoms? Well, it means how many orbitals allowed per shape. And what I mean by that is how many orbitals allowed per S, P, D, and F per shapes. Because those are also zones on the periodic table, but I also told you earlier in the video that these are spherical shapes, the S, and these are dumbbell shapes, the P. And M sub L basically also refers to how many orbitals are allowed per shape. Okay, so let's just do a quick example. Alright, and I'll prove exactly what I'm trying to get across. So let's say n is equal to 2, okay? L means that it could have multiple values. It could be 0 or 1, okay? M sub L, we could do M sub L values for 0, and that would just be 0. And we could do M sub L values for 1, and that would just be negative 1, 0 to positive 1, okay? Each single number that you see, alright, each single number that you see refers to an orbital. So for 0, right, there's only one number, which means that there's only one orbital allowed for that number. And specifically, we learned that 0 corresponds to S, right? And I also told you early in this video that S only allowed for one orbital. It only allowed it for one orbital. Okay. We also learned earlier in this video that 1 referred to P, and that P allowed for 3 orbitals. Well, this is where that's coming from. If we look at negative 1, 0, and 1, that's 3 numbers, which is 3 orbitals. Okay. Now there also is another quantum number known as the spin quantum number. We didn't really get into that, but hopefully you know enough now to maybe go further and learn about the spin quantum number. And I hope this video did a solid job in going over orbitals and different shapes and how the quantum numbers themselves relate to not only the periodic table but how many orbitals there are, and hopefully you get a better atomic relationship between these 3 quantum numbers and not just some mathematical quantum number. Also, I think you know enough by now to go ahead and check out the spin quantum number. Hopefully this helped, and with that being said, I will see you guys later. I really hope this helped.